Well, yeah, first let me thank the organizers for giving me the chance to speak today. It's good to see many of you back again, at least virtually as names in the titles. So the talk will be a little different from what you have heard so far, or at least in the last hours, for two reasons. The first is I'm already fading a little bit into the topic of tomorrow, which is engines. And the second is I'm experimentalist, and that means I have a slightly different viewpoint on many things. And what I want to present today is our approach to realize an engine or engine cycles in ultra-cold gases using quantum statistics. Why do we want to do that? So you all know that engines are important in our daily life, starting from steam engines, as shown here, to cars. And no matter if you burn fuel or use an electric car, that's the heart of society. But as an experimental physicist, we love to make things small. And that means if you start to make things small, you can think about building very small robots, like millimeter-size robots that you have seen here. And you can continue. And probably the most important example to show what is possible gives biology. We have molecular motors, kinesin, dynamin, that carry huge loads in our cells to keep our bodies functional, and that work also with amazing efficiency in our bodies. But you'll know that this is not the end. We can make things even smaller. And at some point, we hit length scales of single atoms and length scales where quantum physics comes into play. And an important question here is, do we get novel properties if we consider single atoms or quantum objects? And can quantum properties maybe even enhance the performance of engine operation in some way? And what I would like to present today is first, since I don't know if you're all familiar with ultra-cold atoms and gases, I will give a very brief introduction in what these objects are and why I experimentally like them so much. And then how we can use quantum statistics to drive an engine cycle and, well, maybe transform some kind of energy into mechanical work at some point. So the people involved in this are, first of all, Jennifer Koch. She is the leading author on that. And Zian Barbosa, he is also a PhD student in that lab. But we had also theory support by Erik Lutz from Stuttgart, and from Okinawa, Thomas Busch and his group, and that is Eloisa Cuestas, Thomas Fogati, and Kirti Menon. And also, I should mention the next generation of PhD students are Felix and Alexander. All right, so what does ultra-cold atoms mean? And I would like to contrast this a little bit against the ambient air that we all breathe at the moment. And if we take, for example, here a temperature scale, a logarithmic one, then our air here is located somewhere between the surface temperature of the sun, a few thousand Kelvin here, and the point where water freezes and becomes solid and forms ice. If you cool this further down, then you can here come to a point where you get liquid nitrogen, or the coldest liquid that we have, that is helium, that can be either a relatively normal classical liquid or a superfluid. But what we produce is orders of magnitude colder here in the range of sub-microkelvin, so fractions of a millionth fraction of a degree above absolute zero. So why do we do this? And one answer to that is we want to make atoms slow. So let's compare the velocities of the mean particle velocities at these temperatures with velocities of ambient air. So if we could pick out a molecule from our ambient air, its velocity would be somewhere between a bullet and a race car. Cooling that down means going down in velocity here through the velocity of a sprinter to the velocity of a turtle at land. And somewhere between that and the velocity of a snail here, that is the velocity that a particle at these ultra-cold temperatures has. And that means cooling down a gas to these ultra-cold temperatures means bringing the velocity into a range where we can easily observe dynamical properties. At the same time, we have to prevent the atoms from becoming solid or liquid. And for this, we rarefy the gas very much. So from our ambient air, we go down a few orders of magnitude just above the particle concentration that you have at ultra high vacuum conditions and a little more than what you have in interstellar space. So few 10 to the 12 particles per cubic centimeter, where the atoms still form many-body rarefied gas, but do not frequently collide so that they could form a liquid or a solid. So what we then gain is we can form a gas that does not obey usual Boltzmann statistics, but where the quantum statistics comes into play. And you all remember from your introductory lectures in quantum statistics that for bosons, Bose-Einstein statistics is the right distribution function. And that means there is an energy of the particles if it matches the chemical potential, where this distribution function diverges and the particles condense all in the ground state of the potential, and that is a Bose-Einstein condensate. For fermions or particle with half-integer spin, the Fermi-Dirac statistics is the right one. And here the particles form a Fermi C due to Pauli principle and fill up all the energy levels up to the Fermi energy. And importantly, if you compare the energies of those two many-body systems at exactly the same temperature, so it's at zero temperature or very close to zero temperature, the energies are markedly different. So for the Bose-Einstein condensate, you have essentially the ground state energy of your trap. But for the Fermi C, you have the Fermi energy, which in metals can amount to huge temperature or huge energies. Compared to temperature, this would be a few thousand Kelvin. So the Pauli principle enforces a huge energy into a many-body system of indistinguishable fermions. And this is something we want to exploit and run some kind of engine cycle from that. Experimentally, we can produce such ultra-cold gases, and because they're so cold, we have to isolate them very well from the ambient air. That is done, as shown here, in an ultra-high vacuum system. Lots of steel, magnetic field coils, and from time to time you see windows where we can look in and shoot in lasers that we use to produce and to manipulate and detect what's going on in these gases. So if you would come to my lab, what you would see is lots of optics here. So this is not the storage space. It's all like aligned to the micrometer. The idea is that you take laser sources, and because light has so many degrees of freedom, like intensity, frequency, the mode diameter, the polarization, we need to adjust this all properly. Once we have adjusted a laser beam as we want it, we feed it into an optical fiber that is here, one of these yellow pipes, and they go across the ceiling to another table. And here there is buried under optics also one of these ultra high vacuum chambers. And the whole lab essentially is only there that in a very small volume of 100 by 100 by 100 micrometers, the right laser beam enters at the right time. All right, so what does it have to do now with engine cycles? And for that, again, let me remind you of something you certainly all remember from your lectures. And let me remind you of the so-called Otto cycle. So in Otto cycle, what you do is, in a periodic fashion, you take a working fluid, you bring in energy, for example, coupling it to a hot bath, igniting some kind of fuel to increase the pressure. Then you allow for adiabatic expansion in some kind of cylinder, and the piston is expelled. That performs work. Then you extract excess heat, or you expel the fumes to go to a lower temperature. You adiabatically compress this again to return to the original initial point. And in this cyclic process, you can convert some kind of heat energy into mechanical work. And the two important figures of merit are the efficiency. So how much work can you extract compared to the energy you put in? And what is the power of the cycle? So how much work can you perform in the given cycle time? And early on, people have realized, and I was a little bit suggestive here to draw harmonic oscillator vessels, that you can also bring this to a quantum regime, quantizing, for example, here the harmonic oscillator, asking the question, what is now different if we have a quantum Otto machine, a quantum Otto cycle? And there is a lot of work going on experimentally and theoretically. And just to mention a few, experimentally, single atom or quantum machines have been realized here in single ions, in spins in NMR systems, or in solid state systems. And also theoretically, much work has been done asking the question, how do coherence, correlation, phase transitions, or non-Markovianity affect the operation of one of these engines, single atom engines coupled to some kind of reservoir? There is in quantum engines an important difference, and that is you have, especially if you look at thermal states, a very peculiar role of fluctuations. And that is, if you look at the quantum state of or quantum properties of a thermal state, then clearly the fluctuations can be shown to be super-Poissonian. And that is not important if you drive, for example, a car on the highway and you always have formed the average of 10 to the 23 particles. But if you have a single particle, this leads to the fact that fluctuations can lead to a very unstable engine operation. And I just want to mention that that is one thing that has been worked on theoretically quite a bit. And that is also something that I'm interested in experimentally. Not so much in this talk, but in some other experiments that I cannot report about today. So now how can we use this knowledge about how an engine works and now form a many-body engine driven by quantum statistics? And the idea is that we would like to replace this bringing in of energy here in the form of heat in the classical Otto cycle, replace this by quantum energy, by going, for example, from a bosonic Bose-Einstein condensate to a fermionic Fermi-C. And just as an illustration, the idea would be that you have two very different pressure states. One pressure state where the particles form a Bose-Einstein condensate and you have a very, very low pressure state. And then going to a high pressure state means going to a system where you have Pauli exclusion principle being active, where the particles want to, well, do not share the same quantum state and thereby increasing the pressure in the many-body system. And now you say, well, that's nice idea, but quantum statistics and the spin state of a system is a very fundamental property of an elementary particle. How could we ever think about changing the quantum statistics of a many-body system? And to this, I have to tell you a little more about the experimental details of how we do this. So what we do experimentally is we cool a lithium gas, and lithium atoms in this specific isotope are fermionic. We can prepare two different spin states that are here labeled as blue and red, and they form a Fermi-C up to the Fermi energy. And that is as you would expect. Due to Pauli exclusion principles, the blue balls or the spin-up states cannot interact with each other, and likewise the red balls cannot interact with each other. But blue and red, or spin-up and spin-down lithium states, can interact with each other. And now one very specific nice feature of the lithium gas is that there exists a so-called Feshbach resonance. That means just tuning a magnetic field, we can change the magnitude of the interaction, but also the sign of the interaction. That is shown down here. That is the so-called S-wave scattering length, or you could imagine it for repulsive interaction as the size of the atoms in a classical picture. And you see tuning the magnetic field in some kind of Gauss is our natural unit in the lab, but it's just turning the knob of a power supply. You can go from almost non-interacting gas to a strongly repulsive interacting gas to an attractively interacting gas. And for these ultra-cold temperatures, you can form very peculiar quantum states. On one side of this resonance, you form molecules and the system condenses in a molecular Bose-Einstein condensate. On the other side, you form Cooper pairs, and it's like a conventional BCS superfluid that you know from conventional superconductors. And right on resonance, you form a so-called unitary Fermi gas, what I would like to discuss in some more detail in a second. So let me introduce one parameter that is very important in this field of interacting Fermi gases. So if you remember your solid state lectures, you can relate the Fermi energy to the Fermi wave vector. And that is just by taking this formula of free particle dispersion in a free fermion gas and relate this to the density of the electron gas, or in our case, of the atomic gas. If you massage this a little bit, this connection between Fermi wave vector and the density, you find that the Fermi wave vector is nothing but a measure of the inverse particle distance. So in a Fermi gas, the inverse or the particle distance is quantified by the Fermi wave vector. Another important quantity to quantify the interaction strength is now the S-wave scattering length, or the size of the particles. And to make a dimensional interaction parameter that allows you to compare very different interaction regimes, you can form the parameter 1 over KFA. And just to illustrate what this means, this parameter, let's have a look at two different values of this 1 over KFA. A very weakly interacting gas is, for example, given by 1 over KFA very large compared to 1. That means you have classically very small atoms that have large distances, so interactions are very rare, very weak. If you now increase the interactions, the classical limit is 1 over KFA equal 1 when the particle distance is as large as the radius or the size of the particles. And that is classically the strongest interaction that you can have. Quantum mechanically, however, because you have wave functions, 1 over KFA can become even smaller than 1 and can become 0. And that is a very peculiar state where you have so strong interactions that all microscopic details of the interactions are not important anymore. And you form a very specific, strongly interacting gas that is described by the same universal functions, no matter if you look at an ultra-cold Fermi gas in our lab, or, for example, in a neutron star, the Fermi liquid of the neutrons forming there. And that means if we have a look at the phase diagram, what is shown here is this interaction parameter 1 over KFA. Here is the temperature, and you see that for all temperatures, if you become cold enough, you form a superfluid, where on the one side you form molecules in a molecular Bose-Einstein condensate. On the other side, you form the BCS Cooper pairs, and in the middle, you have resonant interactions, so very strong interactions of one fermion interacting with many others in this gas. Now, a last missing ingredient will be, how about the quantum statistics behavior along this so-called BEC-BCS crossover? And for this, let me introduce length scales in the system. In the Bose-Einstein condensate, this you can imagine as a quantum liquid. If you excite it gently, you will have sound wave-like excitations. And now you can ask the question, at which length scale does the system cannot respond anymore as a wave? And this length scale is coined a phase coherence length, or the healing length, and that is shown here in yellow. The weaker the interaction, the longer the length scale where the Bose-Einstein condensate can still respond collectively. And if the interactions become larger, then this length scale is getting smaller and the system can respond even on smaller length scales. That is shown here. There is a second length scale, and this length scale here is the pair size, which in the Bose-Einstein condensate is very tiny. So you have tightly bound molecules that are just almost point-like, so very, very small. If we now go towards the resonance, what you see is that this length scale of the wave function response gets smaller and smaller. At the same time, the molecular size or the pair size gets larger and larger. And just as you enter this classically forbidden region of the crossover, the two length scales exchange their role, exchange their relevance. And in the crossover, it's the pair size, which is the larger length scale that dominates the response of the many-body system. And as a consequence, deep in the BEC, if you look in position space, you see a position condensed Bose-Einstein condensate that responds as a many-body wave function. Right on resonance, because the pairs are so large, Pauli blocking forbids the population of single particle states, and you have to form a Fermi sea and Fermi-Dirac statistics is the right quantum statistics that plays a role. And that means for this composite two-body system, you can go from Bose-Einstein statistics to Fermi-Dirac statistics just by tuning here the interaction strength and by tuning magnetic field in the lab. And these are now the ingredients to form a many-body engine. If we could zoom into our setup, what you would see is we have an ultra-cold Fermi cloud that is trapped here in an optical dipole trap and an optical tweezer. And there is a slight magnetic trap in addition. And we take our data by forming just the shadow cast on a CCD camera if we illuminate this cloud by a resonant laser beam. So now this engine cycle is done in a very simple fashion. We again have a compression stroke, and this is done by just compressing the harmonic oscillator trap, going from one trap frequency to another one. Then we have what we call quantum statistics or Pauli stroke, where we go from a Bose-Einstein condensate to a Fermi C. Then we expand again. That is done again by just expanding the harmonic oscillator trap. And then we recondense the system from a many-body Fermi C to a Bose-Einstein condensate. And what I would like to show now is that indeed you can, stroke by stroke, have a look at what you do to the many-body system and that you indeed transform energy from the quantum statistics into the work strokes. Down here is the absorption image of the clouds at the 4 points that are indicated here in this auto-inspired quantum cycle. You see the largest effect comes from the compression, and the quantum statistics stroke is the difference in cloud from point B to point C. And this I have to show now that this indeed has something to do with quantum statistics, that it's really a quantum statistics effect. And to do this, we look at the trap energy. That means how much energy does the atoms, the cloud, the many-body system gain in the trap potential. And that is shown here. So there are many relevant energy contributions. There is the molecular binding energy, the residual interaction energy, the Pauli energy that we're interested in, and the potential energy. The nice thing is that deep in the BEC, we can keep track of all of these, and right at resonance, because the system responds or shows universality, we also can keep track of all these individual energy contributions. And what you see here in green or turquoise is the energy change if we go indeed from a Bose-Einstein condensate to a many-body system. What we can also do is we can change the interaction strength, but always stay in a Bose-Einstein condensate. That means just change the interaction within the Bose-Einstein condensate. And that is shown here in orange, and you see that is a much lower effect. And I would like to point out that this is something that has been realized in the group of David Weld at Santa Barbara in some kind of Feshbach cycle. And they also ran and analyzed in detail one of these interaction-driven cycles. Another indication or proof that this is really associated with a kind of quantum statistics energy is if we run exactly the same cycle as shown here, but now go above the critical temperature. So where quantum statistics should not play a role anymore, but when the system should obey Boltzmann statistics, then we find indeed that there is no effect of this cycle and that this Pauli stroke does not induce any energy change in the system. So that means this Pauli stroke is indeed, or we conclude that this is indeed something that is associated with quantum statistics. And now in the cycle, we can go stroke by stroke and have a look on what the energy is, how the energy changes. If we, for example, change here for the compression ratio in the sample. Again, that is the compression stroke, that is the Pauli stroke. This is the expansion stroke where we can take out energy. And this is the recondensation where returning to the original point, we do not change the energy at all. And from this, we can now also reconstruct some kind of pressure volume diagram. And this is shown here. To guide your eye, there are two dashed lines. The first dashed line is the equation of state for a Bose-Einstein condensate. And the blue dashed line is the equation of state for a unitary Fermi gas. And I would like to point out that groups before that, like 10, 15 years ago, have already measured this equation of state for unitary Fermi gases. And what happens now is that if we compress or expand the cloud, we move on this equation of state. The cloud just changes pressure and volume according to this equation of state. But if we change the quantum statistics, we move from one of these equation of state to the other one. And so the cycle is from going from point A, first compressing the Bose-Einstein condensate, then going to a Fermi gas brings us up here, expanding, that takes out work, and then recondensation brings us back to the original one. And the area that we enclose by this in this pressure volume diagram is now the work that we can in principle extract by this engine. And that is shown here. That is the work that we can in principle output. We cannot in our case because we do not have a system that really can, has a feedback mechanism from the cloud onto, for example, the trap. That is something for the future. But what you see is that there is a significant work of a few million trap frequency or trap oscillation and quanta associated with. And I would like just to point out that here, in this case, the work in principle increases if we go from an interacting Bose-Einstein condensate to a more and more non-interacting gas. And the efficiency, like the work output that we have compared to the Pauli stroke energy, that is also here in the range of a few 10%. But here, interestingly, the efficiency goes down if we go to a non-interacting gas. And the answer intuitively is the work increases because if you start from a non-interacting Bose-Einstein condensate, then you have more cloud expansion potential, so to say, available. If you start from an interacting gas, the cloud is already larger. So therefore, going to a non-interacting gas allows you to have more work per cycle turnover. The efficiency, however, goes down because realizing a non-interacting gas means you have to put in a lot of energy to form molecules or to dissociate them. And therefore, this suppresses the efficiency. And the ideal gas up here, that is the, well, case we cannot realize to really turn a perfect Bose gas into a perfect Fermi gas without any additional energy that we have to put in. All right. So we had a look also here at the work output as a function of atom number. The interesting thing is here, if you look at the curvature of this, then you find that this goes non-linearly with a particle number, which indicates that this non-linearity is a signature of the quantum aspect, and that does not occur for a Feshbach cycle. And also we can run multiple cycles here, where in the end atom losses here suppress a little bit the work output that we can extract. All right, the big question that we have for the future is, can we outcouple work from this device? Can we make something useful with this? And with this, I'm already at the summary. And so my take-home message for you is that indeed we are working on realizing many-body engines that can be driven by quantum forms of energy, in this case, quantum statistics energy. We have an experimental platform now that allows us to address fundamental questions experimentally. For example, shortcuts to adiabaticity, where I not only mean shortcuts to adiabaticity from the compression and expansion, but also if we change the quantum statistics, which is theoretically very challenging to compute, but where we have now an experimental way of really probing the system. And of course, now asking questions like, how does engine operation perform closer across phase transitions is something that we can also now experimentally realize. So that's not the only project where I work on quantum engines. We also have an experiment where we have single impurities in a many-body system, where we realize single atom probes in quantum engines. I would like to make some advertisement for an experiment where we work on realizing a quantum processor with a Rydberg atom tweezer array that is called RIMAX, together with colleagues from Hamburg and Kaiserslautern. And I would like to mention in my group efforts to do NV magnetometry. And what you see here is the tip of an optical fiber, where we can build photonic structures and microwave antennas to build sensors that are as small as a fiber tip to do biological sensing applications. All these people do very dedicated work. That's my group. I thank them for their dedicated, passionate work, and I thank you for your attention. Thank you very much.